Hello again. I think that most people have sorted out their audio, and if you still have troubles doing so, I have posted links in the chat window. So it's about to start, and my name is Magnus Jansson. I am the Market Communication Manager at Westermo. And before I hand over the presentation to our expert, I would like to give a brief introduction to Westermo as well as sorting out a few housekeeping rules. Westermo is a Swedish company that designs and manufactures data communication products for mission-critical systems in physically demanding environments. Our products are used both in social infrastructure, such as transport, water, and energy supplies, as well as in process industries such as mining and petrochemical. We have been in the business since 1975, and as a manufacturer of industrial data communication devices and software, we have gained a lot of knowledge within the company. And today's webinar is an example of what we do to get some of that knowledge out there to you. We develop and manufacture our products in our facilities in Sweden, and we have our own sales and support offices in 12 different countries. We also have distribution partners in another 35 countries around the world. So we have a good global coverage, which is important as we know that a local presence is crucial for many of our customers. More information about the company and our product range can be found on the website, so make sure to visit westermo.com if you want to know more. In today's webinar, we will be looking at how to ensure continued reliable operation of legacy serial remote connections in this webinar that we have titled Serial to IP Migration. To present this topic, you will have Ray Locke, one of our technical experts within the Westermo Network Applications team. Ray has deep knowledge and long experience of industrial data communication technologies, and he has hands-on experience of migrating many old serial systems to modern IP-based solutions. I will hand over to Ray in a little bit. But before I do that, I just want to mention that we are accepting questions, but we will answer them in an email after the webinar is completed. There are many people in the webinar today, and time is of essence. If you have any questions during the webinar, please use the chat window and post your question to host. I will then make sure that the question will be answered right away if I know the answer, but if it's related to the subject, I will make sure that Ray gets it and answer you in an email reply. I just want to mention that you will also get a link to a recording of this webinar. If you want to repeat anything, you will also get access to all the slides as well. I will come back to that in the summary in the end. But it is now time to hand over to Ray. So please, Ray, I will give you the controls and the presentation is yours.
Thanks, Marcus. Good morning, afternoon, evening to all of you, depending on where you are in the world. As Magnus said, I'll just advance the slides here. Serial IP migration. I'm Ray Locke. Some of you may know me, a lot of you may not know me. I've been around the Westermo Group now for about 21 years. In fact, it's my 21st anniversary next month. So a bit of a dinosaur in the organization, but I have had the pleasure, if you like, or the experience of actually dealing with serial technology when it was in its heyday for telemetry systems, as they were called then, or utilities, right the way through to remote access for PLCs, for talking to RTUs, IEDs, basically industry-wide use of serial communications. Over that 21 years, I've seen a massive change in the way that we communicate, going from old serial modems and serial interfacing right the way up to now to 10 gig interfacing for Ethernet. So a bit of a journey for myself. It's been long and interesting, and it always keeps me on my toes. So hopefully today I'll be able to relay some of the information I've gathered over the years to you to show you various ways forward for your applications where you still have serial devices that you want to use into the future. Okay, so why the webinar? Why serial to IP? Why is it important? Well, mostly because regulation and technology shifts are forcing a change in the telecoms market. This is accelerating worldwide. If we look at the use of leased lines, which are literally pairs of wires or two pairs of wires running through the telecom suppliers, the telecom suppliers really do not want to support this any longer. It's old technology, it's very, very bandwidth hungry, and that the copper lines which are used for the delivery of the leased lines could be repurposed and used for broadband, which deliver much higher bandwidth. So essentially, these types of services are being phased out the world over. For example, in the UK, I think now 2022 is the last time, basically British Telecom in the UK will be withdrawing those services. I know already in Germany they've been withdrawn, Switzerland they've been withdrawn, Australia have been withdrawn. So globally, the support for these kinds of services is reducing. Dialup modems are also struggling with the new telecoms systems the world over. What is actually happening in the background, it's not visible to you and I when we actually dial up a user or dial up somebody across the world, but to a modem, the actual infrastructure in between, it doesn't really support dial-up communications any longer. The reason for this is because the background to the exchanges or the telephone system now is really voice over IP. It's not the old kind of telecom systems which were dedicated to carrying voice in a particular way. And the granularity in the interfacing, it just isn't there to support modem communications, because the actual modems themselves actually require a very, very detailed representation of the modem signals to get them across the network. And using voice over IP, everything's compressed, everything's squashed into as small a piece of bandwidth as possible. So you just can't really get the modems to connect. Certainly, it's becoming more problematic. There's an old service for 2G, and sometimes it was available on 3G and 4G, but basically it's also being phased out. It's called CSD, circuit switch data. This is where you can use the actual 2G modems or the wireless networks to dial up and connect using various protocols like V32 and V34. Again, these are all being phased out. There's a unit on the edge of the network, which is basically a huge bank of modems, which pretends to be the connection to the actual wireless modem on the network. It's called an interworking unit. To the best of my knowledge, nobody is producing any of those units any longer. And also, to the best of my knowledge, nobody is supporting those units any longer. So they're being snipped out of the network as fast as they possibly can. So if you're relying on CSD or dial-up over 2G or 3G, then you will shortly find that you will have problems. And you need to be planning for those problems by replacing the service. ISDN has almost completely disappeared now globally. There are some countries which still support it. Essentially, the equipment suppliers are disappearing. The cost of support for those systems and buying spare parts is astronomical now. So over time, in a very short space of time, actually, those services will disappear. And one of the big drivers from our perspective, from the utilities perspective, and for anybody who's monitoring data over a wide area network, big data is becoming the norm. People or companies and regulatory bodies want more and more and more data gathered over a longer period of time, so 24/7 access, 24/7 monitoring of assets, so they can you can get a much better picture of what's going on in your systems and applications. That means that dial-up modems and the use of old lease lines, it just really doesn't deliver the bandwidth which is required for those big data applications. So moving towards a broadband type application is much more the norm now. So as you can get the big data back and get a much better picture of what's going on. All this is against the background of having millions and millions of devices which still support old RS-232, old modems, SCADA systems which are only serial, DCS systems which are only serial. So the whole infrastructure really needs to be updated. Now, it'd be financially impossible for everybody involved in using these old serial devices to actually replace them all with Ethernet devices. So this is how we have to bridge the gap between the old serial world and the new IP communications. And hopefully today's presentation will actually go some way to showing you how this can be done. It's not really in depth. It's there to show you possibilities, give you some ideas about how things work. So hopefully the webinar will show us how to use what we call pseudo lease lines over broadband, which so essentially we're going to emulate what a lease line does, but actually use the internet or the wireless networks or the cellular networks. How the conversion from serial to IP actually works, and why sometimes the differences can actually cause a few issues, and how to get around those issues. Basically, we're going to be talking about the difference between streaming, which is the way the modems work, and packetized data, which is the way IP works, and hopefully give you an appreciation of why there are some differences between the timings and how things actually work, and actually how it can work to your advantage in the future. We'll also look at how ATD dial-up works over IP. Those of you who've got systems which use ATD dial-up, they call a modem the other end of whatever kind. You get a connection, you pass data, you close the call, and then you move on to the next device and call again. We can show you here how that technology can be migrated, again, without the need to change the actual end equipment. You can just use the existing equipment, but change the media in the middle, and everything works, or should work, as it used to. The actual end devices would potentially be completely unaware that the infrastructure in the middle has actually changed to an IP network. At least that's the objective. I'd say we'll also be looking at the potential issues and their mitigations. Okay, so migrating to broadband IP. If we first go backwards and have a look at how modems actually work over a telecom line. In this case, we've got a simple modem-to-modem application. And we've got a SCADA system, which is serial, and we've got a device at the other end, an RTU or PLC, which is also serial. Quite simply, serial packets will pass from the SCADA to the remote PLC and back again over the lease line. It's what was called termed a nailed-up link. Literally, the pair wires have an end-to-end connection between the devices. This could be running over 1 kilometer, or it could be running over 100 kilometers. It really is down to the actual application and the telecom supplier. But when you're using modems, they work in a particular way. They were called the streaming environment, in which case the ones and the zeros, or the serial data, first hits the modem and then gets converted into a series of tones, or actually modulated onto a pair of wires. That modulation process can take between 40 and 120 milliseconds, depending on the type of modem and the type of modulation used. But essentially, it's almost as soon as the bits start coming in, they start getting passed through the process and modulated onto the line. This means that with long messages, that the message itself could actually be partly still being received, partly still online, and then partly being retransmitted to the device at the other end. So it's literally a complete stream of ones and zeros as they pass through the modems. The only real delay is the processing from modem to modem in the middle. And say that's really just happening just as it's coming in, and literally the ones and the zeros get streamed across the link. So the overall delay can be between about 40 and 120 milliseconds. Not a lot of time. If we look at the same thing, look at what we're going to do with lease lines over IP broadband, migrate over, then we'll have, in this case, we'll be using ADSL and VDSL connections to the internet. In this case, the internet becomes our friend, not our enemy. We use it as a media. We're not interested in communicating with any servers or anything in the middle of the network. What we're going to do is establish a VPN, a virtual private link between the two routers on the network. There's that VPN, which is effectively our pseudo lease line or our fake lease line. It's heavily encrypted, so if the encryption's done right and you're using certificates on the VPN, then the actual data within the VPN remains completely secure. Hopefully nobody has discovered how to crack any of the sophisticated protocols which are used. That means that we've effectively got a pipe which runs from, if you like, the router on the right. Let me just get a pointer. The router here to the router over here. Okay, so now we've got our lease line. And now the serial data will quite literally flow through the lease line, flow through the VPN like it would do a lease line. No interruptions to the actual data flow, so we're not being interpreted in the middle anywhere, although there are services which can allow us to actually use routers actually on the internet. That'll be part of another webinar. How a VPN actually works and how the security is built up and how secure the VPN actually is not something we can go into here, but there have been a whole series of other webinars from Westermo about cybersecurity. If you're really interested in how all that works, then look on our website and you'll be able to get some more in-depth information about about cybersecurity and how you can also use firewalls and other means of securing the actual connections end to end. In this webinar, we're purely interested in the serial data. Okay, so what we have here now is effectively a replacement for our modems, a point-to-point connection, just like the previous slides, with a serial device on either end. And quite simply, the serial data will pass from the SCADA system here to the router here. It will get packetized, sent across to this router, stripped out, and then passed on to the PLC. If we break that down into what's actually happening, so Chip mentioned you can also do the same thing over wireless networks, so we're not limited to just ADSL and VDSL. We can also do the same thing with wireless networks, so VPNs are quite happily pass over wireless mobile networks or XDSL, even satellite if you've got satellite connections. In fact, a large part of our business now is in the marine sector, where we have got VPNs which go up via satellites and back down to ground stations and then connect to various routers around the world. So the media, the good thing about the VPNs is they're completely media independent. As long as there's a connection to the internet or there's a connection through between the two endpoints, then you can put a VPN up and say that they're highly secure if they're done correctly with certificates. So how does the serial over IP actually work? As I've kind of mentioned in the last slide, instead of the serial data actually traversing the modems and literally streaming across from modem to modem, within a serial to IP system, you have to packetize the data. And this is where you can get a few time delays occurring. So in this case, the serial data is actually received by the router here. And now it has to receive the message in its entirety. It can do parts, and I'll show you how that can work for you. But usually we wait for the whole message to be received by the router here. We then, if I can just move the slide on, we then packetize the data into an IP packet. So now you've got an IP packet which contains the normal header and header message, saying where it's left from and where it's going to go to. But the payload is actually the serial data which has been gathered by the first router. And that's delivered to the second router over here. When the router has actually received its full message, the full IP packet, which takes a few milliseconds, then the data is actually streamed out of the serial port at the remote location. All this has a time penalty when this is actually taking place. So that raises a potential issue that some systems are actually sensitive to the time delays which can be introduced by using serial to IP conversion. Where does that time delay come from? Which hopefully I'll show you. Okay, if we look at what's actually happening in terms of time, we can see here that we've actually really got two timing zones. There are a few others which are the processing time in the routers, but we'll ignore that for now because it's so only small values. So we'll just look at the big chunks of time which gets used when doing the packetization. Now, the first serial, or the first time delay occurs when we're actually receiving the serial message in the first place. When you look at the actual bytes which are being received, then you're looking at the full length of the message, or the amount of time that the actual message is actually on the wire. So if we got the 100 byte message and it's running at 8 num1, 8 bits, no parity, 1 stop bit, running at 9600, that entire message takes about 104 milliseconds to be received by the first router. Now, that's the first delay. Now, if you remember back to when you're using analog modems, by about 2/3 of the way through that message, even in the worst case, then the modems are starting to actually start to stream the data across to the other modem. So we've already got a little bit of a time delay occurring. Then if we look at the connection between the two routers themselves, now that is a big variable because we're dealing with the internet and we're different with different medias. If we're looking at ADSL to ADSL or VDSL to VDSL connections, that can be around 10 milliseconds, could be about 40 milliseconds. We'll take an average of 40 for this example. If we're looking at 3G, then we could be looking at 300 to 400 millisecond delays, possibly longer. If you're looking at 2G, you could be looking up to 3 seconds. So there are variable time delays in the middle, which introduces an inconsistency or a kind of a variability to the length of time it takes to get over the network. For the purposes of this example, we'll take an average of 40 milliseconds. And then if we look at the other end, we've got a timing value of T3, which is where we're actually going to replay the serial data from which has been received from the IP packet, and then we're going to start streaming that out towards the receiving system on the other side. So if we add all those up together, then we get a delay of 248 milliseconds, which is actually, 2 to 6 times slower than the legacy modem connection, depending on what kind of protocols those old analog modems are using. So we can see here that if you've got a network or a system which is time sensitive, maybe using Modbus, or maybe you're using some other polling protocol, and maybe you've only got a 200 or 300 millisecond window to send and receive the data, then we could start getting close to the edge of what would be classed as a failure in the message type. So it's not a disaster. There are ways around this. So don't lose hope just yet that this is not the way forward, because we've come across this many, many times globally where we've helped customers transition their networks, which have been time sensitive, which have had issues with the variability in the time delays going across the network. These are all solvable problems. You just need to sit down and think about them a little bit and then come up with a solution. So they've all been done before, so it's not as if we're doing this for the first time. Okay. One of the easiest ways to mitigate the timing delays, if you like, is to step up the serial speed. Now, this does require a change to the way that the configuration is made on the remote devices. So in this case, we've got 100 bytes. Now we've set the serial speed up to 57,600 bits per second. This allows you to cut the time on the wire down on the serial side to just 17.4 milliseconds. Now, that's a big change from what it was previously, because it was 104 milliseconds previously. Okay, we've still got the same time constant in the middle, which is 40 milliseconds, but when we replay the message, now we get a reduction in the replay time on the message, which is 17.4 milliseconds. So if you add all those together, now we actually end up with a total transmission time of 74 milliseconds, which is actually faster than the old modems. So now we can see how just a small change to the RTU or to the SCADA system can actually decrease the time on the wire. It has a couple of benefits. One is that there's the timing is much smaller, but it also means that if you've got a big system that you're actually trying to get round and you're having problems reading enough data, and you maybe want to set your scan period to a much smaller value, you can now get a lot more data back in a shorter space of time than you could previously, so you can step your scan rates up. Now, that's one mitigation. That's just simply turning the serial speed up on the system. Another way of mitigating the delays, particularly on systems where you are locked to using a much smaller using a lower baud rate. In fact, I've been dealing with one just at the moment, which is using 1200 bits per second on old serial modems, which is kind of like you can post a letter and get it there quicker at the other end, quicker than you can send in 1200 bits per second. But it's locked, we can't change it. So how do we overcome that timing issue of actually having huge time delays from just receiving messages? Now, the way around this particular issue is, instead of receiving the whole frame and then sending it all in one packet, is to actually receive the data at 5 bytes at a time in this case, and then send the message, break the serial data up into multiple messages to transmit over the VPN. In this case, we're waiting for 5 bytes, so the first message starts to appear after about 5 milliseconds, and then we just add together the time delays again, and you can start seeing that we actually get some very, very small values here. So we're looking at here as the first packet will be sent and received at the other end in about 50 milliseconds. So that's getting to an environment now where it almost emulates what a modem does. It's almost streaming the data across between the routers. The only downside of using this particular methodology is that you end up with a lot of packets which pass over the network. So in terms of data usage, you've got a higher overhead because you're using a few more bytes, but data is becoming cheaper and cheaper on the internet anyway. So even on mobile services, data is getting pretty cheap globally. Funny enough, there is a hidden benefit from this particular methodology. Because you're sending lots of packets between point A and point B, the actual networks themselves will start raising the priority of that data stream because it sees it as a constant stream of data and lots of packets passing through. Particularly on the old 3G networks, this methodology was used always within the 3G. So if the 3G networks see a data stream, they will automatically start pushing them up through the priority stack. So anything with lots of data passing through, or fairly regular data, was actually kept at a fairly high priority level, and therefore the timing across the network dropped. Things which actually are very cyclic, very slow data passing over the network tended to be penalized and slowed down across the network because it wasn't seen as important by the 3G networks. 4G works in a slightly different way, which allows the data to stream across at a fairly consistent rate across the network. And we've got the wonderful word of 5G coming in the future, and heaven knows what's going to happen there in terms of data. It's promising to be a very, very interesting time for us in 5G. Anyway, this webinar is not about 5G, it's all about passing serial data. So we've seen here that we've got a few ways of actually overcoming the issues. Another trick you can use when you're migrating serial to IP environments is that you can start using virtual serial ports on your systems. Now, this is an incredibly efficient way of upgrading the systems across, so particularly in utilities where you have got many, many serial ports and many, many connections going out to hundreds, potentially thousands of sites. In the good old days, you would probably have lots of serial to IP converters, like terminal servers sitting in racks, 19-inch racks in the computer room. And the SCADA will be selecting a serial port to communicate over and then talk down to the remote site and then gather the data and get the messages back and forwards. Very quick tick-tock. Still limited to actually using a serial port at both ends. When you move into the virtual serial port environment, you get away from that whole process of converting, at least at the SCADA end. You get away from the process of converting the creating serial ports via terminal servers, and actually literally move all that technology up into the SCADA system. So you have a program which sits actually on the SCADA server, which emulates or creates virtual comms ports. There is no real limit. I mean, in terms of what you can do with some of the softwares which are available, you can create up to 4,000 COM ports if you really want to. It gets to a point, I guess, where it's impractical to create that many virtual comms ports because you do start using memory and resources and such like in the SCADA system. But if you've got 20, 30, 40 comms ports that you want to replace, physically replace, and then make virtualized, that will quite happily fit into a normal server footprint, and you will be able to get all your virtualization up into the SCADA server itself. Why is that an advantage to you? Well, it does mean that the whole process of converting, sorry, I'm just getting a pointer. The whole process now is much quicker of actually sending the serial data through to the SCADA system, for example. In this case, we're still receiving the serial data here. We will still packetize it and send it to the router here. But instead of the router decrypting deciphering the IP message and then playing it out of its serial port, the whole IP message is passed up to the SCADA here. And it has actually passed straight to the virtual comms port, which means to say that it's actually then available in memory or at the application API layer within the machine itself. So it's literally an electronic transfer of data. There are no replay times using this methodology, which speeds up things tremendously because we've got rid of the replay time actually at the SCADA end of the application. So things have now, timing has basically been halved, or at least reduced significantly from doing a serial to serial replay. You'll find this is much quicker, much easier, much more flexible than using terminal servers and the such like on your systems. Now, here's the animation. So the IP packet and serial data is passed straight to the SCADA system and is used by the application right away. So everything transfers in memory. We can also do the same trick with ATD dial-up emulation. So we look back about how an ATD actual core works. So I've stripped it right down to just the basic connection types. So you've got a serial device which is calling an old analog modem. It sends ATD 1, 2, 3, 4, 5, 6, 7, 8. That is the telephone number of the corresponding modem the other end. So it connects. Then you hear those tones going on while it negotiates what it can do over the line. Hopefully then it gets a connection, and then there's an exchange of data between the SCADA system, for example, and the PLC or the RTU. And then the call is closed using ATH or some hardware handshaking to close the call, and then you get a disconnection. Just the negotiation on that first ATD can take about 20 to 30 seconds of time. So it's quite time consuming to do ATD dial-up communications. And that's a big limiter when you've got a big system you want to get round and do a lot of data gathering across your system. So how can that be emulated, or how can that be replaced? Well, quite literally, we can follow the same process where we can do ATD dial-up emulation, where instead of the serial message calling, forcing the modem to dial a connection the other side, the actual interface within the routers themselves will convert that ATD dial-up stream into an IP address. And that IP address is used to connect to the router the other side, and then establish a connection, or what's called a socket, over the VPN. Once that socket's been established, it will allow the exchange of data in the normal way, and then the calls can be closed in the same way, ATH for hang-up or hardware handshake lines being toggled to actually disconnect. So the whole process looks very similar. The big difference is that this only takes milliseconds to establish connections, exchange data, and then close the call again. So we've saved, when we do this kind of trick on between routers and using a VPN as our dial-up connection, if you like, or our telephone exchange, we actually don't need the 30 seconds in the middle for negotiating the connection. It all takes just a few milliseconds to open the socket and then start exchanging data. You still have the serial time delays going through the system, but the actual initial setup of the connection is much quicker. So that's one way of emulating an ATD dial-up. You can actually go one stage further in that you can run another piece of software, which is called a modem emulator, actually on the SCADA or the DCS or whatever system you're using for your dial-up your dial-up messaging or your data gathering. And that pretends to be a whole bunch of modems at an application layer. It's called a totem pole within the actual applications layer for when these modems are all ganged up one on top of another, if you like, in the memory. But this time when you actually dial, again, you get the ATD, and that's converted to an IP address. But now that opens socket directly to the virtual modems in the SCADA system. And again, what actually happens is that you're able to transfer the serial packet in the first place to the first router, but then it becomes an IP packet as it traverses the whole of the rest of the journey up to the SCADA system. So again, what it's doing is it's actually cutting out a lot of time which would otherwise be occupied with data transfer. The good thing here is that you can create literally hundreds of modems in the virtual memory. So if you want to decrease your scan times on the overall utility system, say you've got 1,000 devices out there and you're not getting round in time using conventional dial-up, by moving to IP, you actually get a benefit in that you can do this dial-up and close calls over 30, 40 lines or 30, 40 connections, if you like, all simultaneously. And because you're actually cutting out the 30 to 40 milliseconds of negotiation time, everything speeds up within the processing of all the data. So you start getting to a point where you can keep on opening and closing ATD connections almost in real time. We've got a few customers who actually do this. They've managed to step their scan rates up. They've improved their servers, admittedly. They've invested in new hardware to cope with all the extra data which is being gathered, but literally brought their scan times down to a fraction of they would be over conventional analog modems. So it's not just a hindrance to actually have to change the technology in the middle. It can actually be a massive benefit to the data gathering process. Scaling up. So far we've looked at fairly small systems where we've been replacing point-to-point connections or simulating point-to-point connections. I've hinted that you can actually scale this up by putting virtualization in place. But there's nothing to stop you quite literally replacing whole utility digitization projects, leaving the serial assets actually in their locations. Because they've still got 10 to 15 years worth of life left. There's no real reason to change them. They're doing the job they're supposed to do. Perhaps they need to report more frequently than once or twice a day, which you could do on the old dial-up systems or leased lines. But now you can actually scale the whole thing up and replace all those modems and then bring all the connections back to routers at the SCADA control room or DCS control room, where you can scan them all from the SCADA system. The scaling up options, use the existing serial ports. So if you already have terminal servers in place which talk to modems or connected to modems, they can all stay. You can literally replace the IP connection, have a lot of modems, a lot of routers receiving point-to-point connections. And basically literally doing a one-for-one replacement. It's kind of an expensive way of doing it, but it can be done if that's what your requirements are. We're actually working with a couple of systems just at the moment which are very, very large and are doing exactly that. They're literally replacing the modems with routers and even keeping the same hardware footprint. You can install virtualization softwares in the SCADA system, which would mean that we can remove all the top-end routers and literally start concentrating all those virtual connections actually in the software level, which makes for a much more efficient transfer of data, cuts down time, increases your scan rates across the whole system, basically speeds the whole process up. If you've got modems and you're actually using dial-up, then you can, say, replace it with virtual modems. Again, we've got customer examples where the existing ATD dial-up modems have been replaced with the modem emulation software, and the whole process has moved up a whole quantum leap in terms of ability to gather data, but still using the existing serial equipment. So it was a win-win for everybody. And some DCS SCADAs, data gathering systems, allow you to use direct addressing. So instead of using a COM port, you will be able to use a IP address for the destination, and the actual SCADA system will encapsulate the requests for data straight into the IP packet. So we don't even need the virtualization. That's down to your particular supplier and a bit of investigation on the actual SCADA system to push things forward. All of which we're quite happy to help and support you through the process of migrating up through and offer advice on the best way of doing it. We looked at how we can now terminate the lease line centrally. Multiple options for scaling up the system, so we can keep as we are, point-to-point connections. We can move into virtualized networks. We can even encapsulate directly from some systems and use the IP layer directly at the application. So again, the big difference with ourselves is we're quite happy to work with you and got years and years of experience in actually migrating these systems up towards a high level of integration with the IP networks and still using serial data. But some questions which are also raised along the way is, well, okay, well, I've got this serial connection. Can I use it for supporting IP devices if I now move over to replacing the serial devices? Well, the short answer is yes. You can move over to a serial application, and you can, I'll just get an annotation up here a second. Here we go. We can start. We can still send the serial data across the network, so no change there. But we can also connect in an Ethernet device into the same router, and we can use direct communication using IP straight through to the SCADA system here. So we can support both simultaneously over the same connection. If we go back to the old analog days with old serial modems, it was practically impossible to do this because there just wasn't the bandwidth and there wasn't the support on the lines to have multiple communications going over, multiple protocols going over the same line. So again, there's a big step change, a big advantage to actually being able to use IP communications as the core. Something not to be scared of. It should be really embraced, and it provides a really, really good way of moving forward for the systems. Okay, if we look at what we can do, okay, in terms of availability. So what we've got here now is instead of just relying on one termination point on the network, because we're moving into the world of IP, then we can start to make use of multiple services within the IP environment. Most of that's to do with routing and resilience, and the ability to dynamically change from one router to another router and seamlessly switch between different endpoints for VPNs. In this particular scenario, let's get the annotation up again. In this particular scenario, I've still got one router at the remote location, but I've actually got two receiving routers actually at the central location. In this particular instance, I'm using two VPNs just for demonstration purposes. You could use one, you could use two. It doesn't really make a lot of difference about the performance of the system. But in this case now, if I lose this VPN, for example, say there's a failure of that particular media pathway, we get an automatic changeover to the second pathway. So now we can increase resilience from the remote location back to the central location. Mainly because this is becoming important, because assets are becoming much more controlled, much more regulated. A good example here is that if you've got leak detection on a water system, which requires 24/7 monitoring and then control of the valves involved in shutting down various sections of the pipework to allow you to stop the leak, then having good control, good reliable control, having two VPNs back to two locations actually increases your availability. I've only shown one at the remote location, but there's no real reason why you shouldn't have two. One of them could be ADSL, another router could be on 3G, and they can work together as well to provide another layer of resistance, so you can have permutations of connectivity. So effectively, we get, through dual pathways, we can actually increase the resilience of the whole network and its overall availability. Because it's usually best to use diversity when you're looking at media. Sometimes if you're using cellular networks, it's using a SIM card from a different cellular provider in each of the routers, or if you've got the ability to use ADSL and VDSL, is to back that up with a 3G connection or a 4G connection. Actually, using 4G in this type of scenario and 3G is actually a very good option, because there's a lot of hidden resilience within the network. If you think about it, there's actually multiple base stations available to you when you're actually connecting a 3G or 4G network. So you haven't just got one base station your connection can go to. As a rule, you've got 2, 3, even 4 or 5 in a city, which allows for a huge amount of diversity within the network. And if you back that up with a roaming SIM or with another router which has got another roaming SIM on, then you end up with a virtually bulletproof connectivity model. One thing to avoid for cybersecurity reasons is SIM cards with static IP addresses. They're not a great idea, and they'll always be discovered. They can be used. Another thing that you can use is an APN, which is an access point name, which is private connectivity over a cellular network. That's being used a lot in utilities. What you should remember there is, according to the cybersecurity standards, IEC 62443, you should still use a VPN even over those services, APN services, because essentially you don't own that particular asset. So you should still use a VPN. I'm kind of straying into cybersecurity here. I said there's another set of webinars about cybersecurity where you can get a lot more information. If I move on to the next slide. Okay, really we're looking at the conclusions now, because I've now kept you for quite a long period of time. Hopefully you found it interesting, but if we look at the conclusions, changing to IP broadband does not mean that the remote devices have to change. We can use the existing RS-232 based devices. They can quite happily migrate over, and in many cases they're not even aware of the change. We don't have to make any changes whatsoever to the configuration or the way they work, which saves time, money, energy, all the plus points of actually migrating over to IP broadband services. Plus, we can get much higher degrees of data gathering, so big data is entirely possible even with serial devices. There's many options to replace and improve on the legacy modems. 3G, ADSL, even over satellite, it all works. Is all highly reliable. Usually the biggest issue is usually time delays, but usually with a little bit of thinking you can overcome all those time delay issues as well. So again, it's a very easy way forward. And considering that the old services are completely dying anyway, it's something which has to be considered. Moving to IP broadband can increase availability. We've seen that we can use diverse pathways to connect remote locations or to central locations. By having media diversity, we actually increase the availability. So if you lose the 3G network dies or the 4G network dies completely, then ADSL is there to take over and vice versa. So huge amount of diversity. We even got some customers who are running corporate network, 3G, ADSL, and then there's one that's actually running satellite as well. So there's if something is super important to communicate with, you can use any kind of media to communicate over, and you're not limited like the old serial days. The operational cost, something I haven't been able to show here, because I was trying to find some information which shows you the difference between the operational cost of running lease lines compared to lining broadband. I do know from customer experience that the actual drop in cost is incredible. If you look at the average cost of a lease line, which can run into thousands of euros a year, and look at the equivalent broadband costs, which are a few €100 a year, then the cost difference is huge. So moving to IP can seem to be daunting to start with, or a big mountain to climb to start with, but actual fact, in terms of the technology, it's all there, well proven. In terms of costing, potentially there's some massive cost savings to be had by actually moving to a broadband connectivity. So there are some supporting documentation on our website, which is, there's a white paper, Migrating Serial to IP. That covers many of the topics I've just been talking here in a much more text and pictorial view. There's older white papers on multi-drop lease lines. There's numerous application notes on our website which show you how even specific devices can be migrated. Allen Bradley PLCs, Mitsubishi, Schneider PLCs can all be migrated over to serial over IP. Even different protocols can be handled in different ways, like DMP3, Modbus, IEC 101, for example. That last element shouldn't be there. Hopefully you found this interesting. If there's a demand, we can run a more in-depth one, covering different portions of actual serial communications. So your feedback is quite important about how you found this seminar or this webinar. And in general, we'd be very interested in your feedback about how we're actually approaching this subject. And okay, if you need more information, please contact me or through the main website. If you've got any questions, please type them in, or you can send an email to information@westermo.com, and we'll get back to you just as soon as we